James Webb looked into a patch of darkness so small, you could hide it behind a grain of sand held at arm's length. To the human eye, there was almost nothing there. No bright star, no glowing planet, no obvious sign that this tiny piece of sky was special. Just darkness. A quiet, ordinary darkness. The kind we pass over every night without thinking. The kind that seems empty because our eyes were never made to see what is truly hiding inside it. But Webb was not built like our eyes. It was built to wait. To gather light slowly, to listen to the faintest signals, to catch the tired glow of ancient things that had been traveling through space long before Earth had oceans, long before the first cell moved in the dark water, long before the sun itself had begun to burn. And when the telescope opened its golden mirror to that tiny patch of night, the darkness did not remain empty. It filled with galaxies. Not one, not a dozen, not a few lonely islands of stars. Thousands. Tiny jewels of light, scattered across the black like dust from some ancient fire. Some were soft and golden. Some were stretched into faint arcs by gravity. Some were red, dim, and almost lost, as if they were trying to disappear back into the beginning of time. Each one was not a star. Each one was a galaxy, a vast city of suns, a structure so large that light itself may need tens of thousands, even hundreds of thousands of years to cross it, a home to gas clouds, star clusters, dust lanes, black holes, and worlds that may never be known. And all of them were hiding in a piece of sky that looked empty. That is the first quiet shock of James Webb. The universe is not empty where it looks empty. The darkness is crowded, but the number of galaxies was not the real problem. At first, it seemed like a triumph, a beautiful confirmation that Webb was working even better than anyone hoped. The telescope had done exactly what it was designed to do. It had reached farther, deeper, and colder than any infrared eye humanity had ever placed in space. Scientists expected distant galaxies. They expected faint galaxies. They expected ancient light. What they did not expect was how mature some of those galaxies seemed to be. Because when you look far enough into space, you are not just looking across distance. You are looking backward through time. The light from a nearby star may have traveled for only a few years before reaching us. Sunlight takes about 8 minutes to arrive at Earth. The glow from the center of our Milky Way takes tens of thousands of years to reach us. But the light Webb was gathering from these deep fields had traveled for more than 13 billion years. Think about that gently. 13 billion years. That light began its journey before Earth existed, before the sun existed, before our solar system had gathered itself from a cloud of dust and gas, before the Milky Way looked the way it does tonight. It left its source when the universe was young, very young. Not young in the way a mountain is young, not young in the way Earth was once young in a cosmic sense. The universe was still in its early morning. The first stars had only recently begun to shine. The first galaxies were still supposed to be small, rough, and unfinished. Gravity was still gathering gas into clumps. Matter was still learning how to build structure. In the story scientists had carefully assembled over decades, the early universe should have looked messy. Small galaxies, dim galaxies, irregular shapes, little clumps of stars trying to hold themselves together, a universe under construction. If the modern universe is a vast city at night, filled with shining towers and glowing roads, then the early universe should have been a field of foundations. A few lights, a few frames, the first outlines of what would one day become something grand. But Webb looked back toward that early field and saw buildings already standing. Not everywhere, not in every image. Not enough to throw away everything we know, but enough to make scientists pause, enough to make them check the numbers again. Because some galaxies at the edge of Webb's vision were brighter than expected. Some seemed larger than expected. Some appeared to contain more stars, more dust, or more chemical richness than the old timeline comfortably allowed. And that is where the phrase begins to make sense. It's not good. Not because there is danger coming toward Earth, not because the universe is ending, not because Webb found something evil waiting in the dark. It is not good for our old assumptions. It is not good for the simple version of the story. It is not good for the comforting idea that we already understood how the first galaxies formed. For years, the universe had a timeline, a slow timeline. First, the Big Bang, then a hot, glowing fog, then atoms, then darkness, then the first stars, then tiny young galaxies, then bigger galaxies, then clusters, then spirals, then planets, then much later, us. A long rising staircase, step after step after step. But Webb is showing us places where the staircase seems to have missing steps. It is as if the universe skipped ahead, as if the first chapter of cosmic history was not as quiet, not as slow, and not as simple as we once believed. And that is a strange feeling, because the farther Webb looks, the younger the universe should appear. But some of what Webb sees does not feel young. It feels busy. It feels bright. It feels strangely awake. Imagine walking into a nursery and finding adults standing there, speaking in calm voices. Imagine opening a book to the first page and discovering that half the story has already happened. Imagine arriving at dawn and finding a city that somehow built itself during the night. That is the feeling Webb has given to modern cosmology. Not panic. Something quieter than panic. A deep scientific unease. Because science is not frightened by being wrong. Science is built to be corrected. But there is a special kind of silence that happens when a powerful new instrument shows you the universe more clearly than ever before. And the universe does not look the way your best equations said it should. That silence is where this journey begins. Out there, nearly 1 million miles from Earth, James Webb drifts in the cold, behind its silver sunshield, with its golden mirror turned toward darkness. It does not hurry. It does not sleep. It waits for ancient photons, one by one, each carrying a memory from a time when the cosmos was still becoming itself. Some of those photons left galaxies that may no longer exist in the form we see them. Over billions of years, they may have merged, stretched, collapsed, changed, or vanished into larger structures. We are not seeing them as they are. We are seeing them as ghosts, real ghosts, made of light. And those ghosts are whispering something uncomfortable. They are saying the early universe was not empty. They are saying the darkness was not still. They are saying the first galaxies may have grown faster, burned brighter, and gathered themselves sooner than we thought possible. This is why Webb's view of the universe's edge matters so much. It is not just a photograph. It is a test of time, a test of gravity, a test of how stars are born, a test of how black holes grow. A test of whether the first light in the universe followed the story we wrote for it. And already, the answers are not simple. Some scientists think the galaxies may only appear too massive because hidden black holes are making them shine brighter than their stars alone would allow. Some think star formation in the early universe may have been far more efficient than expected. Some think dust, gas, and ancient stellar populations are confusing the measurements. And some wonder whether the first cosmic structures formed under conditions we still do not fully understand. None of these possibilities is small. Each one changes the story. Each one opens another door, and Webb has only just begun to look. That is perhaps the most haunting part. The telescope has not finished its work. It has not delivered the final answer. It has not closed the mystery. It has opened it. Every deep field is another window. Every red dot is another question. Every ancient galaxy is another message from the time before the sun. And as we drift deeper into this story, we have to remember something important. James Webb did not find the end of the universe. It found the edge of what we can know with light. And at that edge, the universe did not appear quiet. It appeared crowded. It appeared awake. It appeared older than it should. So tonight, we begin with a tiny patch of darkness. A darkness small enough to vanish behind a grain of sand. A darkness that should have been simple. But when Webb looked closer, it became a doorway. And through that doorway, we will follow the oldest light we have ever seen. Toward galaxies that formed too soon, black holes that grew too fast, and a universe whose first morning may have arrived earlier than anyone expected. Because the deeper Webb looked, the younger the universe became, but the galaxies did not. When people hear the phrase, the edge of the universe, it is easy to imagine a wall, a final border, a place where space simply stops. Maybe a dark curtain stretched across the end of everything. Maybe a silent boundary where the stars end, where galaxies fade away, and beyond it, there is nothing left to see. But the universe does not seem to have an edge like that. At least, not one we can point to. There is no known wall at the end of space, no cosmic cliff, no final line where a spacecraft could arrive and look over the side. The edge James Webb is looking toward is stranger than that. It is not the edge of space. It is the edge of sight, the edge of time, the edge of what light has had enough time to bring us. Because the universe may be much larger than what we can observe, it may extend far beyond the horizon of our instruments, far beyond the oldest light that has ever reached Earth. There may be galaxies so distant that their light is still traveling toward us and will not arrive for billions of years. There may be regions so far away that their light will never reach us at all, because space itself is expanding too quickly between us and them. So when we say Webb is looking at the edge of the universe, we are really saying something more delicate. Webb is looking toward the edge of the observable universe, the part of reality whose light has finally made it here. And that is what makes the view so haunting. The farther away something is, the longer its light has been traveling. Light is fast beyond anything human life can easily imagine. In 1 second, it can circle Earth more than 7 times. It can cross from the moon to us in just over a second. Sunlight, warm on your face, left the surface of the sun about 8 minutes before you felt it. So even when you look at the sun, you are looking into the past. Only 8 minutes, yes, but still the past. Look at Jupiter, and you are seeing it as it was tens of minutes ago. Look at the nearest stars, and you are seeing years into the past. Look toward the center of the Milky Way, and you are looking back tens of thousands of years, to light that began its journey when early humans were still walking under ancient skies. But Webb looks much farther. It looks beyond the Milky Way, beyond nearby galaxies, beyond the great clusters and filaments of the modern cosmos. It looks to places where light has been traveling for more than 13 billion years. That means Webb is not seeing those galaxies as they are now. It is seeing them as they were when the light left them. A galaxy whose light has traveled for 13 billion years is not a picture of the modern universe. It is a message from a universe that was almost unimaginably young. Since that light began its journey, entire galaxies have changed shape. Stars have been born and have died. Black holes have fed and gone quiet. Planets have formed from the ashes of older stars. On one small planet, oceans appeared, continents moved, life began, eyes evolved, and eventually those eyes built a telescope to catch the ancient light, all while the photon kept traveling, silently, patiently, across expanding space. This is why deep astronomy feels almost impossible to hold in the mind. A telescope is not only a machine for seeing distant places, It is a machine for seeing earlier times. The night sky is not arranged in one single present moment. It is layered. Every star, every galaxy, every faint red smudge is a different time arriving at your eyes all at once. Nearby stars show us a younger past. Distant galaxies show us a deeper past. And the farthest galaxies show us the childhood of the universe. But there is another complication. The universe is expanding. Space itself is stretching. And as space stretches, the light traveling through it stretches too. Imagine drawing a small wave on the surface of a rubber band. If you pull the rubber band slowly apart, the wave becomes longer, its peaks spread out. Its shape changes, not because the wave itself decided to change, but because the thing carrying it was stretched. Light behaves in a similar way. The first galaxies gave off light that may have been ultraviolet or visible when it began its journey. But for billions of years, that light traveled through expanding space. Its wavelength stretched longer and longer. By the time it reached our region of the universe, much of it had shifted out of the range human eyes can see. It became infrared, invisible to us, invisible to many older telescopes, but not invisible to Webb. That is why James Webb is not simply a bigger telescope. It is a different kind of eye. Hubble showed us the universe mostly in visible and ultraviolet light, with some infrared ability. It revealed galaxies, nebulae, deep fields, and structures that changed astronomy forever. But Webb was designed for the ancient light that Hubble could not easily catch. Webb was built for infrared, for the stretched light of the first galaxies, for the soft, cold glow of objects hidden behind dust, for signals so faint that even the telescope itself had to become almost impossibly cold, so its own warmth would not drown them out. Out near a point in space called L2, nearly 1 million miles from Earth, Webb stays shielded from the heat of the sun, Earth, and Moon. Its broad sun shield unfolds like a silver kite in the dark, keeping the golden mirror and scientific instruments cold enough to hear the universe whisper. And the whisper it listens for is ancient, not loud, not dramatic, not like an explosion, more like a fading note from the beginning of a song, a note stretched by time, thinned by distance, dimmed by expansion, but still carrying information. Inside that light is a record. How bright the galaxy was, how hot its stars were, what elements were present, how fast it may have been forming stars, how much dust surrounded it, whether something hidden, perhaps a black hole, was adding its own glow. This is what makes Webb so powerful. It does not only take pictures. It reads light. Every color is a clue. Every missing wavelength is a clue. Every faint red signal is a clue. And because the light is so old, every clue is also a timestamp, a measurement of how the universe behaved when it was young. But the word young can be misleading. When we say a galaxy existed only a few 100 million years after the Big Bang, that may still sound like a long time. Hundreds of millions of years is longer than the entire history of human civilization by a factor so huge it becomes almost meaningless. It is longer than dinosaurs ruled Earth. It is longer than mountains rise and disappear. But in cosmic history, a few 100 million years is early. Very early. The universe today is about 13.8 billion years old. So when Webb observes galaxies from only a few 100 million years after the Big Bang, it is seeing the universe when it was just a small fraction of its current age. A cosmic infant. And that infant universe was supposed to be simple. Not empty, exactly, but unfinished. It should have been full of hydrogen and helium, with the first stars beginning to gather in small pockets of gravity. It should have been rough and dim, like the first sparks before a fire fully catches. The first galaxies should have been fragile things, small, chaotic, still assembling, still poor in heavy elements, still learning how to become the grand structures we see today. But Webb's ancient light has made that picture less comfortable, because in some of those distant signals, scientists are finding signs of brightness, structure, and activity that seem to belong to a later time. Not everywhere. Not in a way that destroys everything, but enough to make the early universe feel less like a nursery and more like a place where something had already been working very hard in the dark. This is the quiet tension at the heart of Webb's discoveries. The edge is not a wall, it is a horizon, and every horizon hides what lies beyond it. When Webb looks toward that horizon, it is not asking, where does space end? It is asking, how did the first light begin? And the answer coming back is not simple, because the first light does not look as faint as expected. The first galaxies do not all look as small as expected. The first cosmic structures may not have waited as long as expected. Somewhere, in that deep red glow, the early universe is giving us a timeline that does not perfectly match the one written in our textbooks. And this is where the journey becomes more than beautiful. It becomes uncomfortable. Imagine hearing a story your whole life about how a great forest grew. First seeds, then sprouts, then thin young trees, then, after a very long time, a mature forest. Then one day, you find a photograph from the forest's first morning. And in the photograph, some of the trees are already tall. That does not mean the forest is impossible. It means the story is incomplete. Something helped those trees grow faster. Something in the soil, something in the weather, something in the first light, or something we have not yet named. That is what Webb is showing us at the edge of sight. Not an ending, not a wall, but an old photograph from the first morning of the cosmos. A photograph where the shadows are crowded, the light is too bright, and the youngest galaxies do not all look young enough. And as Webb keeps watching, the question becomes harder to avoid. If the telescope is truly seeing the universe as it was only a few 100 million years after the beginning, then why is there already so much light? Why are there already so many galaxies? Why do some of them seem to have grown up before the universe had time to grow old? That is the next mystery. Not the edge itself, but what was shining there. Because when Webb looked past the darkness, past the redshift, past the limit of ordinary sight, it found too much light, too early. At the beginning of everything we can see, the universe should have been dim, not completely dark forever, but dim, quiet, unfinished. A place where gravity was still gathering the first clouds of hydrogen, where the first stars were only beginning to burn, where galaxies were still small and uncertain, like sparks trying to survive inside a cold wind. This was the picture scientists expected James Webb to find. A young universe. A fragile universe. A universe still learning how to shine. And Webb did find that. In many places, it saw exactly what the models predicted. Faint little galaxies, stretched red by time, glowing softly from a period when the cosmos was still young. These were the kinds of galaxies astronomers hoped to study, the first building blocks, the early seeds that would later merge into the grand spirals and giant ellipticals we see today. But hidden among them were others, brighter ones, stranger ones, galaxies whose light seemed too strong for their age, galaxies that appeared when the universe was only a few 100 million years old, and yet somehow looked as if they had already gathered enough stars to become serious structures. Not finished like the Milky Way, not calm like a mature spiral galaxy, but too bright, too active, too present. And that is the phrase scientists kept circling back to in different ways. Too early, because in cosmology, time is not just a background. Time is an ingredient. You need time to form stars. You need time for gravity to pull gas into dark matter halos. You need time for gas to cool, collapse, fragment, ignite, and build stellar populations. You need time for the first massive stars to live their short, violent lives and explode. You need time for their ashes to mix back into the gas, enriching it with carbon, oxygen, nitrogen, and dust. You need time for galaxies to grow from small clumps into something brighter and more complex. The early universe was not supposed to have much time yet, and still, Webb saw light. A lot of it. Some of this light came from galaxies so distant that their glow began its journey when the universe was less than 300 million years old. To a human mind, 300 million years sounds vast. It is longer than the age of many mountain ranges, longer than the time since the first dinosaurs walked across Earth. But to the universe, it is a first breath, a newborn hour. The cosmos today is about 13.8 billion years old, so a galaxy, shining at 200 or 300 million years after the Big Bang, is not a galaxy from the middle of history. It is a galaxy from the opening moments. It is almost at the first page. And yet some of these first-page galaxies do not look as faint as expected. One of the most distant confirmed galaxies Webb has revealed is a soft red signal from a time when the universe was only a few 100 million years old. Its light is not dramatic in a photograph. It does not arrive like lightning. It does not look like a monster. It is just a faint, reddish smudge, a quiet mark, a nearly invisible ember in the dark. But to astronomers, that ember carries a problem. Because for something to be seen from that distance, across that much expanding space, it must have been shining with surprising strength. Either it had more stars than expected, or its stars were hotter and more efficient than expected, or something hidden inside it, perhaps a young feeding black hole, was adding extra light. Whatever the answer is, the result is the same. The early universe was producing visible structure faster than the simplest version of the story allowed. Imagine standing before a long road at sunrise. You have been told the city at the end of the road is still under construction. There should only be scaffolding there, some wooden frames, a few lamps, maybe the first workers arriving in the cold morning. But through a telescope, far away in the pale light, you see windows already glowing. You see streets. You see towers. You do not know yet whether the buildings are as large as they appear. Maybe some of the light is distorted. Maybe the windows are brighter because of fires inside. Maybe the air itself is bending the view. But you cannot ignore what you see. There is too much light. Too early. This is what Webb has done to the story of cosmic dawn. It did not simply discover that early galaxies existed. Scientists already expected them. The deeper question is how many there were, how bright they were, and how efficiently they were able to turn raw cosmic gas into stars. In the old picture, the first galaxies were supposed to be small and inefficient. They formed from pristine gas, mostly hydrogen and helium, with almost no heavy elements. Heavy elements help gas cool. Cooling helps gas collapse. Collapse helps stars form. Without many heavy elements, star formation should have been harder, slower, less efficient. But Webb's distant galaxies suggest that some early systems may have been forming stars with surprising power. The furnace was already burning. The factory was already working. The darkness was already being filled. And every time astronomers pushed deeper into the data, the same question returned in a new form. How did they turn on so fast? There are possible explanations. There always are. Science does not stop at surprise. It starts there. One possibility is that these galaxies are not actually as massive as they first appear. Light can be misleading. A galaxy with a hidden active black hole at its center can shine far brighter than its stars alone. If astronomers mistake that extra black hole light for starlight, they may overestimate how many stars the galaxy contains. In that case, some of the impossible galaxies become less impossible. Not ordinary, but less impossible. Another possibility is that the first stars were very different from stars today. The first generation of stars may have been enormous, hundreds of times more massive than our sun, burning hotter, brighter, and faster than modern stars. A small number of such stars could produce a large amount of light, making an early galaxy appear unusually bright, even if it did not contain as much total stellar mass as it seems. A third possibility is that star formation in the early universe was simply more efficient than our models assumed. Maybe gas flowed into the first galaxies more smoothly. Maybe dark matter halos gathered material faster. Maybe radiation feedback, the process that normally slows star formation by pushing gas away, did not regulate the first galaxies in the same way. Maybe the early universe had a rhythm we have not yet learned to hear. This is the careful version of the mystery. Not that physics is broken. Not that the Big Bang is wrong. Not that the universe made a mistake. But that our recipe may be missing something. We thought we knew how fast the first structures could grow. Webb is showing us that the answer may be faster. And that changes the feeling of the beginning. Because the first light in the universe was not only beautiful, it was powerful. It was not just a few lonely stars turning on in a sea of hydrogen. It may have been a rapid awakening, a rush of formation. A deep cosmic morning where stars, galaxies, and perhaps black holes all began working together sooner than expected. This matters because the first galaxies shaped everything that came after. They made the first heavy elements. They began clearing the cosmic fog. They created the environments where later generations of stars and planets could form. They were the ancestors of all the bright structures we see tonight. Even the atoms in our bodies are connected to that early light. The carbon in your cells, the oxygen you breathe, the iron in your blood. None of it existed in the very beginning. It had to be made inside stars. It had to be forged, released, mixed, and reused. The universe had to build chemistry before it could build rocky worlds. It had to build stars before it could build life. So when Webb shows us galaxies shining earlier than expected, it is not just adjusting a number in a chart. It is moving the first pieces of the entire cosmic story. If stars came earlier, chemistry came earlier. If chemistry came earlier, planets may have had ingredients earlier. If black holes grew earlier, they may have shaped galaxies earlier. And if galaxies formed efficiently in the first few 100 million years, then the universe did not spend its childhood waiting quietly in the dark. It began building almost immediately. That is why the images feel so strange. They are peaceful to look at. Soft red dots, faint arcs, tiny glows in black space. Nothing in them screams. Nothing moves. Nothing appears dangerous. But underneath that silence is a pressure on time itself. A question placed gently against the foundations of modern cosmology. How young can a galaxy be and still look old? The more Webb looks, the more the answer seems to shift. Not always dramatically, not always in the same way, but enough that scientists can no longer treat the first galaxies as simple, dim, predictable things. They were not just sparks. Some were engines, some were furnaces, some may have hidden black holes inside them, some may have been wrapped in dust, some may have been forming stars in ways we do not yet fully understand. And somewhere among those first lights, the universe began to reveal the shape of a deeper problem. The problem was not darkness. The problem was not absence. The problem was abundance. There was too much light, too many early candidates, too much activity, too much structure appearing close to the beginning. And for a telescope designed to look back toward the first cosmic dawn, this is both a triumph and a warning. A triumph because Webb is doing exactly what it was built to do. It is showing us the hidden universe. It is catching the red-shifted light of galaxies no human eye could ever see. It is reaching into a time that once belonged only to equations and imagination. But a warning, because the universe it reveals is not neatly following the path we prepared for it. It is brighter. It is faster. It is more crowded. It is more alive with formation than expected. And this is where "it's not good" becomes more than a title. It means the beginning was not as simple as we hoped. It means the first galaxies may not have been quiet little islands, slowly gathering themselves in the dark. It means the universe had already started writing complex chapters before we thought the ink was dry on the first page. And Webb is still reading. Photon by photon. Red smudge by red smudge. Ancient galaxy by ancient galaxy. Out there, in a silence colder than any night on Earth, the golden mirror keeps turning faint light into questions. And the questions are growing. If there was already this much light at the edge of time, then what was powering it? Was it only stars? Were the first stars more massive than we imagined? Were galaxies better at forming them than our models allowed? Or was something darker hiding in their centers, feeding, glowing, and helping the young universe shine before it should? That is where the story must go next. Because light was only the first problem. The next problem was time, and the universe should have needed much more of it. The universe should have needed more time. That is the quiet problem sitting underneath Webb's deepest images. Not just more space, not just more matter, not just more stars, more time, because nothing in the universe becomes complex all at once. A galaxy is not simply born as a galaxy. It has to be built, slowly, patiently, from ingredients that are almost too simple to imagine. In the beginning, after the first fire of the Big Bang had cooled, the universe was mostly hydrogen and helium, the lightest elements, the simplest atoms. There were no planets yet, no dust grains, no carbon-rich clouds, no oxygen drifting between stars, no iron, no silicon, no calcium, no gold. The early universe did not begin with chemistry as we know it. It began almost empty of complexity. A vast ocean of simple gas, expanding, cooling, waiting for gravity to begin its work. And gravity is patient. It does not build in an instant. It pulls gently, constantly, silently. A region of gas just slightly denser than the space around it begins to attract more gas. The more gas it gathers, the stronger its gravity becomes. The stronger its gravity becomes, the more gas it can gather. This is how structure begins. Not with a sudden command, but with a slight imbalance. A whisper in the density of the young universe. A tiny region with a little more matter than its surroundings becomes a seed. Around that seed, dark matter gathers into a hidden halo. Ordinary gas falls into the halo. The gas compresses, it heats, it cools, it breaks into clumps, and inside some of those clumps, the first stars ignite. That sounds simple when spoken quickly, but each step takes time. And time is exactly what the early universe did not have much of. The first stars were probably not like our sun. They may have been enormous, hot, unstable, and short-lived. They formed from almost pure hydrogen and helium, without the heavier elements that help modern gas clouds cool and fragment into smaller stars. Because of that, many scientists believe the first stars may have grown to monstrous sizes, perhaps tens or hundreds of times the mass of the sun. They would have burned with a violent blue-white light. They would have poured radiation into the surrounding darkness. And they would have died young. A star like our sun can live for about 10 billion years, but the most massive stars live fast. Some burn through their fuel in only a few million years. They shine intensely, then collapse, explode, and throw their newly forged elements back into space. This is how the universe began to change. The first stars were not only lights, they were factories. Inside them, hydrogen fused into helium. In the cores of the most massive stars, heavier elements began to form: carbon, oxygen, neon, magnesium, silicon, iron. Then, when those stars died, their explosions scattered those elements into the gas around them. For the first time, the universe had ashes, and those ashes mattered, because the next generation of stars would not form from pure hydrogen and helium alone. They would form from gas that had been touched by the dead, gas enriched by the first stars, gas that could cool more efficiently, collapse more easily, and create smaller, longer-lived stars. With each generation, the universe became more chemically complex. First stars, first deaths, first heavy elements, first dust, first enriched clouds, first second-generation stars, then more galaxies, then more explosions, then more enrichment. This is a cycle, and cycles require time. That is why Webb's discoveries are so uncomfortable, because when it looks back into the first few 100 million years, it is not only seeing galaxies, it is seeing signs that some regions of the early universe may have already gone through more of this cycle than expected. A young galaxy is one thing. A young galaxy that is bright is more surprising. But a young galaxy that seems chemically active, dusty, or unusually developed is something deeper. It suggests history, and history needs time. Think of a forest after a fire. At first, there is only black ground and ash. Then, small green shoots appear. Then young trees. Then, after years and years, shade returns. Birds return. Roots deepen. The soil changes. The forest becomes layered, rich, alive. If you walked into that forest 1 week after the fire and found tall trees, thick moss, fallen logs, birds nesting, and deep soil already formed, you would not say the forest was impossible, but you would know the timeline was wrong. Something had happened earlier. Something had moved faster, or the photograph was not what you thought it was. This is the kind of question Webb is raising. The early galaxies may not be impossible, but they are asking for a better clock. A better story of how quickly matter can organize itself when the universe is young, dense, and full of flowing gas. One clue is star formation. A modern galaxy like the Milky Way forms only a few stars each year on average. It is still alive, still making stars, but it is no longer young and frantic. It is more like a city that continues to build new homes slowly, after its main streets and towers are already in place. But some early galaxies seem to have been forming stars far more rapidly. Dozens, hundreds, perhaps even more solar masses of stars each year, depending on the object and the interpretation. In a young universe, that is extraordinary. To make stars that quickly, a galaxy needs fuel. It needs cold gas falling inward. It needs gravity to hold that gas. It needs conditions that allow clouds to collapse again and again without being completely blown apart by the radiation of the stars they create. But stars resist their own birthplaces. When massive stars ignite, they flood their surroundings with radiation. Their stellar winds push gas away. Their supernovae explode violently, heating and scattering the material nearby. This is called feedback. And feedback is one of the universe's natural breaks. It prevents galaxies from turning all their gas into stars at once. It regulates growth. It makes galaxy formation slower, messier, more balanced. But in Webb's early universe, some galaxies seem to have pressed hard against that break. They kept forming stars. They kept shining. They kept growing. So either feedback worked differently in the first galaxies, or gas was flowing in so quickly that the galaxies could keep feeding their star-forming regions, even while young stars were trying to blow them apart. That is one possible answer. The early universe may have been better at delivering fuel. Dark matter halos may have pulled gas inward more efficiently. Cold streams of gas may have flowed along the invisible skeleton of the cosmic web, feeding young galaxies like rivers feeding a newborn sea. Instead of forming slowly in isolation, these galaxies may have sat at intersections where matter was constantly arriving. A galaxy in such a place would not have to wait quietly. It would be fed, again and again. And if the first stars were unusually massive, they could have changed the story even faster. Their light would be intense. Their deaths would be violent. Their explosions could spread heavy elements quickly through the surrounding gas. Their shock waves could compress nearby clouds, triggering more star formation instead of only stopping it. A chain reaction. One generation ignites. It dies. Its death enriches the gas. The enriched gas forms more stars. Those stars die too. The galaxy grows brighter. The universe becomes less simple. All inside a window of time that, until Webb, seemed too narrow. This is where the mystery becomes beautiful. Because the question is not only, how can this be? It is also, what was the early universe really like? Maybe it was not a slow, sleepy place. Maybe it was not a dim fog waiting calmly for stars to appear. Maybe it was a storm. A deep, quiet storm. Not loud in the way storms are loud on Earth. There was no air to carry thunder between galaxies, no sound traveling through the void. But gravitationally, energetically, chemically, the first few 100 million years may have been far more intense than our old picture suggested. Gas rushing along dark matter filaments. First stars burning with enormous brightness. Supernovae exploding into pristine clouds. Black holes beginning to feed. Radiation carving bubbles into hydrogen fog. Galaxies assembling at the intersections of invisible structure. The first morning of the universe may not have been gentle. It may have been rapid, crowded, bright. And that changes how we understand everything after it. Because if the first galaxies matured faster than expected, then the entire cosmic timeline becomes more flexible. The first heavy elements may have appeared earlier. Dust may have formed earlier. Planet-building ingredients may have spread earlier. Black holes may have influenced galaxies earlier. The cosmic fog may have cleared earlier, or in a more uneven way. And the path from simple gas to complex structure may not have been a slow staircase. It may have been a series of sudden rises. Long, quiet stretches, then bursts. Darkness, then fire. Stillness, then growth. For decades, astronomers had a picture of the early universe that made sense. It was not perfect, but it was elegant. It said that small things formed first. They merged into larger things. Galaxies grew over time. Chemistry built up generation by generation. Complexity increased slowly. That picture is still broadly true. But Webb is showing that the details may be far more intense. The first galaxies may have been smaller than they look, or brighter because of black holes, or powered by stars very different from those we see today. The measurements are difficult. The distances are extreme. The light is faint. Scientists are cautious for a reason. But even after caution, the unease remains. The early universe looks productive. Too productive in some places. Too efficient. Too awake. And that is why time itself becomes the mystery. If you see a single bright galaxy early, you might call it rare. If you see several, you begin asking questions. If each deeper survey reveals more candidates, more red glows, more signs of early structure, then the question grows larger. Maybe the universe did not need as much time as we thought. Maybe our models underestimated how fast the first cosmic engines could run. Or maybe something hidden was helping them. Something with gravity strong enough to gather gas. Something capable of shining without stars. something that could sit at the center of a young galaxy and make it appear brighter, more energetic, more mature than it truly was. A black hole. Not the quiet black holes drifting in isolation, but young, feeding black holes. Ancient monsters beginning their growth while the universe itself was still young. Because if the galaxies seem too early, the black holes are even harder to explain. A galaxy can grow quickly if gas flows in fast enough. But a black hole has a speed limit. It can feed only so fast before its own radiation pushes matter away. And yet, in the early universe, Webb and other telescopes have found signs of black holes that appear far too large for their age. That is the next layer of the problem. The light was too early. The chemistry was too early. The galaxies carried hints of history too soon. And in the deepest centers of some of them, the darkness itself may have been growing faster than time should allow. At the center of many galaxies, there is a darkness so heavy that even light cannot escape it. A black hole. Not a hole in the ordinary sense, not an empty tunnel, not a doorway leading somewhere else, at least not in any way science can yet confirm. A black hole is a place where matter has collapsed so completely that gravity becomes stronger than escape itself. Cross too close, and there is no return. Not for gas, not for dust, not for planets, not even for light. And in the centers of large galaxies, these black holes can become enormous. The Milky Way has one. It is called Sagittarius A star, and it sits at the heart of our galaxy, hidden behind thick clouds of gas and dust. It contains the mass of about 4 million suns. Around it, stars move in fast, tight orbits, revealing the invisible weight at the center by the way they dance. 4 million suns sounds almost impossible, but in the universe, Sagittarius A star is not the largest. Some galaxies contain black holes millions, hundreds of millions, even billions of times the mass of the Sun. These are supermassive black holes. They sit like dark anchors in the centers of galaxies, shaping the motion of stars, heating gas, and sometimes powering some of the brightest objects in the cosmos. When a black hole is quiet, it is almost invisible. But when it feeds, it can outshine its entire galaxy. Gas falling toward a black hole does not simply disappear, not at first. It spirals inward, forming a hot, glowing disk called an accretion disk. The gas rubs against itself. It heats to extreme temperatures. It shines in ultraviolet, X-rays, and infrared. Magnetic fields twist. Jets may launch from near the center at nearly the speed of light. The black hole itself is dark, but the meal around it can blaze. These feeding black holes are called active galactic nuclei. The most luminous of them are quasars. Some quasars are so bright that they can be seen across billions of light years, like cosmic lighthouses shining from a time when the universe was still young. And this is where the problem begins. Because James Webb, along with other powerful observatories, is revealing that very massive black holes existed extremely early. Too early for comfort. Less than 1 billion years after the Big Bang, some black holes already seem to have grown to hundreds of millions, even billions of solar masses. In human terms, 1 billion years sounds endless. But in cosmic terms, it is not much time at all. And some of the most troubling black hole candidates come from even earlier windows, when galaxies themselves were still young, still forming, still wrapped in gas, dust, and the red glow of cosmic dawn. How does darkness grow that fast? That is the question. A black hole grows by consuming matter. Gas falls in. Stars wander too close. Smaller black holes merge. Over time, mass increases. The black hole becomes heavier. Its gravitational reach expands. But this process is not unlimited. A black hole cannot simply eat the universe around it as fast as it wants. When gas falls inward and heats up, It releases radiation. That radiation pushes outward. If the black hole feeds too aggressively, the light from its own accretion disk can push incoming gas away, cutting off the meal. This creates a kind of natural feeding limit, a speed limit for growth. It is known as the Eddington limit. The details are mathematical, but the idea is gentle enough to picture. Imagine trying to pour water into a bowl while a strong wind blows upward from inside the bowl. Pour slowly, and the water can fall in. Pour too fast, and the wind throws much of it back out. A feeding black hole creates its own wind of radiation. The more it eats, the brighter it shines. The brighter it shines, the harder it becomes to keep eating. So growth takes time. A black hole born from a dead massive star might begin with perhaps tens of solar masses. To grow from that into a billion solar mass monster requires either a long period of steady feeding, many mergers, an unusually massive starting point, or some way around the usual speed limit. The early universe may not have offered enough time for the simplest version of that growth. And yet, the black holes are there, or at least, the signs of them are. Bright, compact sources, ancient quasars, strange red objects, galaxies whose light may be partly powered by something hidden in their centers. This creates a double mystery. The early galaxies seem to grow quickly, and inside some of them, the black holes may have grown even faster. Two clocks running too fast at the same time. That is why astronomers are considering several possibilities. The first possibility is that the first black holes were born bigger than ordinary black holes. In the modern universe, many black holes form when massive stars die. The star collapses, and what remains may be a black hole with several times, or perhaps dozens of times, the mass of the Sun. But in the early universe, conditions may have allowed something more dramatic. Massive clouds of primordial gas may have collapsed directly into black holes, skipping the ordinary star stage. Instead of forming a star, burning, dying, and leaving behind a small seed, the entire gas cloud could have fallen inward under gravity and created a much larger seed black hole from the start. This idea is called direct collapse. It is one of the most important possible answers to the early black hole problem. A direct collapse black hole could begin not with 10 suns of mass, but with thousands, tens of thousands, perhaps even more. That would give it a head start. It would not need to climb the entire mountain from the bottom. It would begin halfway up. But direct collapse requires special conditions. The gas cloud must avoid fragmenting into stars. It must stay hot enough, dense enough, and smooth enough to collapse as one great body. Radiation from nearby stars may be needed to prevent the gas from cooling too quickly. The environment must be rare and precise. So direct collapse may explain some early black holes. But can it explain all of them? That remains uncertain. The second possibility is that early black holes fed faster than the normal limit for at least some periods of time. This is called super Eddington accretion. In special conditions, gas may fall into a black hole in thick flows or along narrow streams, allowing some material to keep falling even while radiation escapes in other directions. The black hole may not shine evenly in every direction. The feeding may be messy, uneven, chaotic. If enough gas keeps reaching the center, the black hole can grow faster than the simple textbook limit suggests. The early universe may have been perfect for this. Gas was abundant, galaxies were dense, mergers were frequent. Dark matter halos were still gathering material rapidly. The centers of young galaxies may have been crowded, unstable, and rich with fuel. A young black hole in such a place would not starve. It would be surrounded, fed by rivers of gas, hidden inside dust, growing in darkness. But again, this answer has limits. Feeding faster than normal may happen, But sustaining that rapid feeding long enough to produce billion solar mass black holes is difficult. The process may turn itself off. Radiation may clear the gas. Explosions and jets may disturb the galaxy. The black hole needs a feast that lasts. The third possibility is mergers. If many smaller black holes formed early, they could sink toward the centers of young galaxies and merge. Each merger adds mass. In a dense early universe, mergers may have been more common than they are today. Two black holes become one. Then that one finds another, and another. Slow growth by feeding could be helped by sudden jumps through collision. But mergers alone also face a timing problem. You still need the first black holes to form early. You need them to find each other. You need them to merge efficiently. And you need all of this to happen while the universe is still very young. No explanation is simple. Each one solves part of the puzzle, then opens another door. That is what makes these ancient black holes so important. They are not just objects, they are clocks. Their masses tell us how much time, fuel, and gravity must have been available in the first billion years. And if the clock does not fit, then our understanding of the early universe needs to change. Maybe the first stars were different. Maybe the first black hole seeds were much heavier. Maybe gas flowed inward more efficiently. Maybe black holes and galaxies grew together in a tight feedback loop, each shaping the other from the very beginning. In the modern universe, galaxies and black holes seem deeply connected. Larger galaxies often host larger central black holes. The mass of a galaxy's central black hole appears related to the properties of the galaxy around it. Somehow, over cosmic time, the growth of galaxies and the growth of their black holes became linked. But Webb is pushing that relationship back toward the beginning. It is asking whether the connection was already there. Were black holes passengers inside the first galaxies? Or were they engines? Did galaxies form first, then feed black holes at their centers? Or did early black holes help shape the galaxies around them, heating gas, stirring matter, triggering or stopping star formation? This is one of the deepest questions Webb has opened, because a black hole can be both destructive and creative. It can tear apart matter, but it can also shape a galaxy. Its radiation can clear gas away, slowing star formation. Its jets can heat surrounding material, but under some conditions, those same outflows can compress gas clouds and help new stars form. A black hole is not simply a cosmic drain. It is part of a system, a dark heart inside a city of stars. And in the first galaxies, those hearts may have started beating earlier than expected. That possibility changes the meaning of the deep red galaxies Webb sees. Some of them may not be bright only because of stars. Some may be bright because a young black hole is feeding inside them, hidden, wrapped in dust, adding its own light to the galaxy's glow. If that is true, then some of the early galaxies that first appeared too massive may not contain as many stars as we thought. Their brightness may be partly an illusion created by active black holes. This would soften the galaxy problem, but it would strengthen the black hole problem, because then we would have to explain why so many black holes were already active so early. The mystery does not disappear. It moves, from the stars to the darkness, from the galaxy to its center, from too much light to too much gravity. And perhaps that is why Webb's discoveries feel so haunting. Every answer seems to reveal a deeper question beneath it. If the galaxies are too bright, maybe black holes are helping. If black holes are helping, then black holes must have formed early. If they formed early, then what made them? Massive stars? Direct collapse? Something else? Step by step, the story moves backward, toward the first stars, toward the first gas clouds, toward the first dense places in the universe, toward the moment when gravity began turning simplicity into structure. And somewhere in that darkness, The seeds of the largest black holes may have been planted. No one has seen those seeds directly yet. Not clearly, not finally. But Webb is getting closer. It is finding candidates. It is measuring spectra. It is separating starlight from black hole light. It is looking for the fingerprints of accretion, dust, ionized gas, and high-energy radiation. It is not just asking what shined. It is asking what fed. And that question becomes even stranger when we return to the tiny red objects scattered across Webb's deepest images. They do not look like much. Small, red, compact, almost modest. They are not great spiral galaxies. They are not glowing nebulae. They are not dramatic cosmic monsters in the way we imagine them. They look like embers. But some embers hide fire. And these tiny red objects may be one of the most important clues Webb has found. Because if they are what some scientists suspect, they may represent a missing stage in the growth of early black holes. A stage where the black hole is still buried, still young, still feeding inside a thick cocoon of gas and dust. Before it becomes a quasar, before it reveals itself, before the universe knows what is growing in the dark. And so the journey continues. From the first galaxies that shined too early, to the black holes that grew too fast, to the little red dots that may connect them both. Tiny sparks at the edge of time, quiet, red, and unresolved, waiting in Webb's data like clues left behind by the first monsters in the universe. At first, they did not look important. Not like spiral galaxies, not like glowing nebulae, not like the great arcs of gravitational lensing, stretched across space by the weight of invisible matter. They were small, faint, red, scattered through the darkness like tiny embers left behind after a fire no one remembered seeing. Astronomers gave them a simple name, little red dots. It sounds almost gentle, almost harmless, like something a child might notice in a painting of the night sky. But in Webb's deepest images, some of the smallest things may be carrying some of the largest questions. Because these little red dots are not ordinary stars. They are not nearby planets. They are not simple errors in the image. They are distant objects. Ancient objects. Compact objects. And their light has been stretched by the expansion of the universe until it falls into Webb's infrared vision, glowing red, not because they are close and warm, but because they are far away and old, very old. Their light comes from a time when the universe was still young, when galaxies were only beginning to gather, when the first great structures had not yet settled into the cosmic web we see today. And yet, these dots shine with a strange intensity. That is the first problem. They are small in the image, but bright for how far away they seem to be. It is like seeing a candle across an ocean and realizing, from the distance alone, that it cannot be a candle. Something much more powerful must be burning there. But what? That is where the mystery deepens. At first, scientists considered familiar possibilities. Maybe they were dusty young galaxies. Maybe they were star-forming regions packed tightly together. Maybe they were distant quasars, powered by black holes feeding at their centers. Maybe they were something in between. But the more Webb looked, the harder it became to place them neatly into any box. They were too compact for normal galaxies, too numerous for ordinary quasars, too red to be simple young star systems, too bright to ignore. They seemed to live in a strange middle ground, not quite galaxies as we usually understand them, not quite exposed black holes, not quite anything modern astronomy had seen in such numbers before. And this is exactly the kind of discovery Webb was built to make. Not only the beautiful things, not only the expected things, but the quiet things hiding between categories. The universe does not organize itself for our convenience. It does not label its objects. It does not tell us which chapter we are reading. It simply sends light, and we have to learn how to understand what that light is saying. The little red dots are saying something, but they are speaking softly. One leading idea is that many of them may be young black holes hidden inside dense cocoons of gas and dust. Picture a black hole in the early universe, not yet revealed as a bright blue quasar, not yet powerful enough to clear its surroundings completely. Around it is a thick shell of material, gas falling inward, dust heated by radiation, young stars forming nearby, all packed into a small, intense region. The black hole feeds. The accretion disk shines, but the direct light cannot easily escape. It is absorbed by the surrounding dust, softened, transformed, and re-emitted in infrared wavelengths. From across 13 billion years, Webb sees this as a small red glow. A dot, a tiny ember, but inside that ember may be a black hole growing in secret. If this is true, then the little red dots could represent a missing stage in black hole evolution, a hidden childhood of quasars. Before the black hole becomes one of the brightest objects in the universe, perhaps it spends time buried, swollen with gas, wrapped in dust, growing behind a curtain. And Webb may be catching that stage for the first time. This would be extraordinary, because it would help explain how supermassive black holes appeared so early. Maybe they were not rare accidents. Maybe many young galaxies carried buried black holes at their centers. Maybe the early universe was full of small red cocoons where darkness was feeding before it became visible. But this explanation creates another problem. There may be too many of them. If every little red dot is a rapidly growing black hole, then the early universe may have been producing active black holes far more efficiently than models predicted. That would change how we understand the first galaxies, the first stars, and the radiation that helped clear the cosmic fog. The solution becomes another mystery. That is how Webb's discoveries often work. They do not close doors. They open deeper ones. Another possibility is that some little red dots are not black holes at all, but extremely dense star clusters or compact galaxies filled with unusual stellar populations. Maybe the first stars and early galaxies produced light in ways that do not match the galaxies we see nearby today. Maybe their stars were hotter, heavier, more crowded, or more dust-covered. Maybe the physics of star formation inside these early systems created colors and brightness patterns that look strange only because we have never observed that era clearly before. In that case, the little red dots might be telling us not about black holes, but about the first generations of stars. They might be laboratories from cosmic dawn, tiny, distant rooms where the universe was experimenting with light. But that answer also has difficulty. To make so much light from stars alone, these compact objects would need extreme star formation. Their gas would have to collapse rapidly. Their stars would have to form efficiently. Their dust would have to absorb and reshape the glow in just the right way. Again, the early universe would have to be more productive than expected. So no matter which explanation is correct, the message is similar. Something in the early universe was working fast. Stars, black holes, dust, gas, maybe all of them together. The little red dots may be small, but they belong to the same larger pattern Webb keeps revealing. Too much light, too much activity, too much growth, too soon. And perhaps this is why they feel so haunting. They do not announce themselves with grandeur. They do not dominate the deep field images. They sit quietly in the background, red and unresolved, like punctuation marks in a sentence we have not learned how to read. But science often changes because of small things. A faint wobble in a star reveals an unseen planet. A slight shift in starlight reveals the expansion of the universe. A tiny temperature pattern in ancient radiation reveals the structure of the Big Bang. And now, small red dots in Webb's infrared images may reveal a hidden phase of cosmic history. A phase when galaxies and black holes were growing together in the dark. Imagine drifting through the early universe, long before Earth existed. There is no blue planet yet, no moon, no Milky Way as we know it. only young galaxies forming in deep space, surrounded by streams of gas, lit by massive stars that live fast and die violently. In some of those galaxies, at the center, something dark begins to grow. It pulls gas inward. The gas heats. Dust forms around it. Radiation struggles to escape. From nearby, it might be chaotic, a storm of gravity, heat, and falling matter. But from across the universe, through billions of years of expanding space, all of that violence becomes quiet. A little red dot. That is one of the strange beauties of astronomy. The most violent places in the cosmos can arrive at our telescopes as silence. No sound, no motion, just color, just a faint glow on a detector, just a question. And the question is not only what these dots are. The question is what they were doing to the universe around them. If many little red dots contain feeding black holes, then those black holes may have helped shape early galaxies. Their radiation could heat surrounding gas. Their outflows could stir matter. Their energy could either slow star formation by blowing gas away, or trigger it by compressing nearby clouds. They may also have contributed to reionization, the great transformation when the first powerful sources of light burned away the neutral hydrogen fog between galaxies. Stars were almost certainly major players in that transformation, but black holes may have helped. And if the little red dots are buried black holes, then Webb may be seeing some of the hidden engines that help the universe become transparent. Small red dots, ancient engines, quiet clues. This is why they matter so much. They connect the mysteries. They connect the bright early galaxies to the oversized black holes. They connect star formation to dust. They connect cosmic dawn to the clearing of the fog. They may be the missing bridge between the first stars and the first quasars. And still, they remain unresolved. Not because Webb is weak, but because the universe is distant and the signal is delicate. Scientists need spectra, not just images. They need to split the light apart and read its fingerprints. They need to know whether the glow comes from stars, hot dust, ionized gas, or accretion around black holes. They need to compare models, test assumptions, observe more objects, and wait for the data to sharpen. For now, the little red dots remain one of Webb's most beautiful uncertainties. And uncertainty is not failure. It is where discovery lives before it has a name. At the edge of the observable universe, these tiny red points are waiting. They may be young galaxies. They may be buried black holes. They may be the first stage of something we have not fully imagined yet. But whatever they are telling us that the beginning of the universe was not simple. It was not empty. It was not slow. It was filled with hidden engines, faint signals, and small red lights that should not be underestimated. And if those red dots really are young black holes wrapped in dust, then they may have helped turn the universe from a foggy darkness into something transparent. They may have been part of the first sunrise, because after the first stars began to shine, the universe still had one more veil to lose. A vast fog of hydrogen, a cosmic mist between galaxies. And somehow, in the first billion years, that mist began to clear. The first morning of the universe had arrived. But now Webb is asking whether that morning came too fast. Before the universe was filled with galaxies, it was filled with fog. Not fog like the mist that rises above a cold field on Earth. This was not made of water. It was made of hydrogen. A vast, invisible ocean of neutral hydrogen, spread between the first forming galaxies, drifting through space before the universe became fully transparent to the light of stars. There had already been one great clearing before this. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to join together and form atoms. Before that moment, light could not travel freely. It scattered again and again inside a hot, dense plasma, trapped in a glowing fog. Then atoms formed. Space became transparent. and the oldest light we can still detect today began to travel. That light is the cosmic microwave background, a faint afterglow of the early universe, stretched by expansion until it now reaches us as microwave radiation, coming from every direction in the sky. But after that first great release of light, something strange happened. The universe entered darkness. There were atoms. There was space. There was gravity. But there were no stars yet, no galaxies shining, no planets, no nebulae, no bright cities of suns. Only hydrogen and helium, slowly gathering under the pull of dark matter, slowly falling into invisible wells of gravity, slowly preparing for the first fires. This period is called the Cosmic Dark Ages, and the name is beautiful because it is almost literal. The universe was not empty, but it had not yet learned how to shine again. There was matter everywhere, but no starlight to reveal it. Gravity was working silently. Tiny differences in density, born from the earliest moments of the cosmos, began to grow. Slightly denser regions pulled in more matter. Dark matter halos formed, gas fell inward, clouds compressed, and somewhere, in one of those deep young wells of gravity, the first star ignited. No human eye saw it. No planet existed nearby to watch it rise. There was no sky in the way we know the sky. But that first star changed everything. For the first time after the Dark Ages began, the universe had a source of new light. Then came another, and another. The first stars may have been enormous, far more massive than most stars today. They likely burned hotter, bluer, and more violently. They lived short lives, but while they lived, they poured powerful ultraviolet radiation into the gas around them. That radiation began to attack the hydrogen fog. Neutral hydrogen is simple, one proton, one electron. But ultraviolet light can strike a hydrogen atom with enough energy to tear the electron away. When that happens, the atom becomes ionized. This process is called ionization. And when it happened across the universe, slowly, unevenly, bubble by bubble, scientists call it reionization. Reionization was not a single flash. It was not one switch turning on. It was more like sunrise moving through a valley filled with mist. At first, only a few patches clear. A bright star forms here. A young galaxy glows there. Around each source of intense light, a bubble of ionized hydrogen begins to expand. Inside the bubble, ultraviolet light can travel more freely. Outside it, the fog remains thick. Over time, the bubbles grow. They overlap. They connect. The mist thins. The darkness changes. And eventually, the universe becomes transparent enough for starlight and galaxy light to travel across vast distances. This was one of the most important transformations in cosmic history. Before reionization, the universe was difficult to see through. After it, the universe became the kind of universe telescopes can study, full of distant light, distant galaxies, and long paths through space. The first morning had arrived, but now James Webb is asking a difficult question. Did that morning come too fast? Because the speed of reionization depends on what was producing the light. You need enough powerful radiation to clear the hydrogen fog. Stars can do this. Young galaxies can do this. Feeding black holes can do this. But the timing matters. If the first galaxies were small, dim, and inefficient, then clearing the fog should take longer. The bubbles of ionized gas should grow slowly. The universe should remain partly opaque for a long stretch of its early life. But if Webb is finding more bright galaxies than expected, if some of those galaxies formed stars very efficiently, if buried black holes were already feeding inside them, if little red dots are signs of hidden engines glowing in the dark, then the early universe may have had more sources of ionizing radiation than scientists once assumed. More lamps in the fog, more fires at dawn, more engines turning on before the timeline said they should. This is why the mystery of early galaxies connects directly to the first morning of the universe. The galaxies were not just passive objects sitting in the dark. They changed the darkness. Their stars burned holes through the hydrogen mist. Their radiation carved out transparent bubbles. Their black holes, if present, may have added even more high-energy light. Their supernovae stirred the gas and spread the first heavy elements. Each early galaxy was not only a structure, it was a force, a small island of light, expanding its influence into the surrounding fog. And if there were more of these islands than expected, then the map of cosmic dawn changes. The fog may have cleared earlier in some places, more unevenly in others. The first light may have been patchy, violent, and strangely efficient. Not one calm sunrise, but many scattered sunrises, blooming across the dark. This is what Webb is beginning to reveal. It sees galaxies from the era when this transformation was still unfolding. It sees faint red objects whose light has traveled from the edge of time. It sees signs of star formation, ionized gas, dust, and possibly active black holes. And in those signs, the old picture becomes less certain. Maybe reionization was driven mostly by countless small galaxies, too faint for older telescopes to see. Maybe it was helped by rare but powerful young galaxies, brighter than expected. Maybe black holes, hidden in the centers of early systems, contributed more than we thought. Maybe the first stars were so massive and hot that they cleared their surroundings with extraordinary speed. Or maybe all of these answers are true at once. That is often how the universe works. Not one cause, a harmony of causes. Gravity gathers the gas. Stars ignite. Black holes feed. Radiation escapes. Supernovae explode. Dust forms. Gas flows again. The fog clears. And the universe becomes visible. But if this harmony began earlier, faster, or more intensely than expected, then the beginning was not the slow, quiet dawn we imagined. It was a rapid awakening, a darkness filled with sudden fires. There is something deeply strange about that, because when we look at Webb's images, they do not feel violent. They feel calm. A black background. Tiny red dots. Soft galaxies. Long arcs of light. Everything appears frozen, peaceful, almost dreamlike. But that peace is an illusion created by distance. Those faint smudges were once places of enormous energy. Stars were forming. Gas was collapsing. Radiation was tearing electrons from atoms. Black holes may have been feeding behind dust. The universe was changing its own transparency. It was becoming see-through. And Webb is watching that transformation, not as it happens now, but as it happened more than 13 billion years ago. A memory of the first morning. A sunrise so ancient that Earth did not exist to receive it. When that light began traveling, there were no oceans here. No continents. No moon in our sky. No humans sleeping under stars. There was not even a sun. And yet, across all that time, across all that expansion, the light survived. It crossed the young universe. It crossed the growing cosmic web. It passed through ages of galaxy formation, through the birth of stars and planets, through the long, quiet assembly of the Milky Way, until finally it reached a golden mirror floating in the cold beyond the moon. And there, Webb caught it, not as a sunrise in the sky, but as data, a faint red signal, a spectrum, a clue. That is the beauty of this telescope. It turns ancient morning into information, and the information is telling us that the first dawn may have been brighter, faster, and more crowded than expected. This does not mean the universe is broken. It means the early universe was more complex than our simplified story. The fog may not have lifted evenly. The first galaxies may not have behaved gently. The first stars may have burned with a power we are only beginning to understand. And the first black holes may have been present not as late arrivals, but as early participants. The darkness was not empty. The fog was not silent. The first morning was already full of hidden engines. And this brings us back to the title of the journey. What Webb saw at the universe's edge is not good. Not good for the old timeline. Not good for the idea that the beginning was slow and simple. Not good for the comforting belief that we had already placed the first galaxies, first stars, and first black holes in their proper order. Because if the first morning came too fast, then something in the story is missing. Maybe the first stars were different. Maybe the first black holes were born heavy. Maybe early galaxies were fed by cold rivers of gas. Maybe dark matter shaped structure more efficiently than we realized. Maybe the universe was ready to build sooner than we thought. Whatever the answer is, Webb has made one thing clear. The beginning was not passive. It was active. The universe did not wait long to become luminous. Soon after darkness fell, light began searching for a way through. And once it found one, the fog started to burn away. Slowly at first, then faster, until the cosmos became a place where galaxies could see each other across the dark. A place where light could travel for billions of years. A place where, much later, a small planet could form around an ordinary star, and beings on that planet could wonder where the first light came from. Now we have sent a telescope into the cold to ask that question. And the answer is coming back in red. Faint red galaxies. Little red dots. Ancient red light, stretched by time. All of it whispering the same possibility. The universe woke up earlier than we expected. And the first morning may have been far brighter than our theories were ready to see. So now we can return to the phrase that brought us here. It's not good. But we have to be careful with those words. Because the universe is not sending us a warning in the human sense. There is no storm coming from the edge of space. No ancient galaxy is threatening Earth. No black hole from cosmic dawn is moving toward us. The light Webb sees has already traveled for more than 13 billion years. The galaxies that sent it may have changed beyond recognition. Some may have merged into larger galaxies. Some may have been torn apart. Some may have become part of structures so distant and evolved that we will never see their present form. There is no danger in those red dots. No danger in those ancient galaxies. No danger in the first morning of the universe. The danger is to our certainty. That is what is not good. Not good for the clean version of the timeline. Not good for the simple idea that we already understood how darkness became light. Not good for the belief that the first galaxies were small, slow, and easy to explain. James Webb did not look at the edge of the observable universe and find the end of everything. It found something more unsettling. It found the edge of our understanding. And at that edge, the story becomes less smooth. For decades, cosmologists had built a powerful picture of the universe's history. It was not a guess. It was not a myth. It was supported by the cosmic microwave background, by galaxy surveys, by the expansion of the universe, by the abundance of elements, by the large-scale structure of space. The model worked beautifully in many ways. It still does. That matters. Webb has not erased modern cosmology. It has not thrown away the Big Bang. It has not proven that everything is wrong. The universe is not broken. But the details are under pressure. And in science, pressure is where the next discovery begins. The old picture said that the first galaxies should grow gradually. Gas falls into dark matter halos. Stars ignite. Feedback slows the process. Small galaxies merge into larger ones. Heavy elements build up over generations. Black holes grow by feeding and merging. The fog of hydrogen clears over time. Step by step. A cosmic staircase. But Webb is showing us places where the steps may be closer together than expected. Places where light appears early. Places where galaxies seem active early. Places where chemical enrichment may have happened fast. places where black holes may already be feeding, places where small red objects hint at a hidden population we barely understand. None of this means the staircase is gone, but it may mean we drew it too slowly. Maybe the early universe was not a sleepy construction site. Maybe it was a dense, efficient, restless place, where gas flowed quickly, stars formed in bursts, black holes grew behind curtains of dust, and the first galaxies became luminous before our models were ready for them. This is what Webb is forcing scientists to ask. How fast can the universe build? How quickly can simple gas become a galaxy? How early can black holes begin to matter? How much light did the first stars produce? How efficiently did young galaxies clear the cosmic fog? And perhaps most importantly, what did we leave out? That is the quiet fear in the phrase, "It's not good." Not fear of the universe. Fear that the story is incomplete. Science is comfortable with incomplete stories. Every theory is a map, and every map leaves out some detail. But the early universe is not a small corner of the map. It is the foundation. It is where everything begins. Change the beginning, and the changes echo forward. If the first galaxies formed faster, then the first heavy elements may have spread sooner. If the first heavy elements spread sooner, then dust and complex chemistry may have appeared earlier. If black holes grew sooner, then they may have shaped galaxy evolution from the very start. If the first sources of radiation were more numerous or more powerful, then reionization may have unfolded differently. And if reionization unfolded differently, then our view of the first billion years has to be rewritten with more care. It is like discovering that the first chapter of a book is not wrong, exactly, but missing pages. And those missing pages may explain why the rest of the story looks the way it does. That is why Webb's discoveries are so exciting and so uncomfortable at the same time. They do not give us a clean answer. They give us a better mystery. Some scientists think part of the problem may come from measurement. These objects are extremely faint and extremely distant. Their light has been stretched, dimmed, filtered through cosmic dust, and interpreted through models. A small error in estimating distance, brightness, dust, or black hole activity can change how massive a galaxy appears. So caution is necessary. Some early galaxies that first looked impossibly massive may become less massive after better data. Some may be bright because of hidden active black holes rather than billions of ordinary stars. Some may have unusual stellar populations that make them shine more strongly without requiring as much mass. In other words, some of the tension may soften. But not all of it disappears. Even when scientists correct, revise, and remeasure, Webb still seems to show an early universe that is busy. More galaxies than expected in some surveys. Bright sources at extreme distances. Compact red objects that do not fit easily into older categories. Evidence that the first cosmic engines turned on with remarkable efficiency. So the mystery survives. It changes shape. It becomes more precise. That is how real science moves. The first headline may be dramatic, impossible galaxies. Then the data improves. The claim becomes more careful. Surprisingly bright galaxies, unexpectedly efficient star formation, possible black hole contamination, early compact sources, revised models. The mystery becomes less theatrical, but more real. Because a mystery that survives better data is stronger than a mystery built only on surprise. And Webb's early universe is becoming exactly that kind of mystery. Not a collapse, a challenge. Not a disaster, a correction. Not the end of cosmology, a new beginning for cosmology. This is the emotional center of our journey. The universe at its edge is not frightening because it is hostile. It is frightening because it is honest. It does not care what story we expected. It does not adjust itself to fit our equations. It simply is. And when we build a telescope powerful enough to see more clearly, the universe gives us what is there, not what we hoped would be there. Not what would make the textbooks easier. What is there? And what is there, at the deepest edge of Webb's sight, appears to be a beginning more active than we imagined. A beginning with too much light, too many early structures, too many hidden engines, too many signs that the darkness was already changing. This is not bad news for humanity. In a deeper way, it is wonderful news. It means the universe still has the power to surprise us. It means the first chapter is not closed. It means the story of how everything began is still alive, still being rewritten, still waiting in faint infrared light. Somewhere in Webb's data, there may be answers that explain all of this without breaking the larger model. Maybe early stars were hotter and more massive. Maybe black holes were born from direct collapse. Maybe early gas flows were smoother and colder. Maybe feedback behaved differently in small young galaxies. Maybe many little red dots are a hidden growth phase of black holes. Maybe several of these things happen together. The universe rarely chooses only one path. It builds with everything available: gravity, gas, radiation, dark matter, time, chance. And from those ingredients, it made the first galaxies. The strange thing is not that we do not yet understand every detail. The strange thing is that we ever thought the beginning would be simple. A universe that can build galaxy clusters, black holes, stars, planets, oceans, forests, eyes, and telescopes was probably never simple at any stage. Even in its youth, it may have been deep with complexity. Even in darkness, it may have been preparing light. And so, when we say what Webb saw is not good, we mean something quiet and profound. It is not good for overconfidence. It is not good for easy answers. It is not good for the idea that the first billion years were just a slow prelude to the real universe. Because Webb is showing us that the prelude may have been filled with music we never heard before. Faint music, ancient music. Red shifted into silence. And now, for the first time, we are beginning to listen. The golden mirror turns toward the dark. A photon arrives. Then another. Then another. Each one older than Earth. Each one carrying the memory of a galaxy, a star, a cloud of gas, a hidden black hole, or a tiny red dot from the dawn of time. And together, they whisper the same uncomfortable truth. We were not completely wrong, but we were not finished. The universe is older in its behavior than it is in its age. It is younger in time, but richer in structure. It is closer to the beginning, but farther from simplicity. That is what James Webb found at the edge. Not the end. Not the answer, but the place where certainty becomes wonder. And maybe that is what the edge of the universe was always going to show us. Not a wall, not a final darkness, but a beginning we misunderstood. And so we return to the darkness where we began, a tiny patch of sky, a place so small that, to the human eye, it would seem like nothing at all. No sign, no warning, no doorway, only blackness. But James Webb looked into that blackness and found memory. Not memory like ours, not thoughts, not dreams, not stories held inside a mind. This was memory made of light, ancient light. Light that left its home before Earth had formed, before the sun had ignited, before the atoms in your body had gathered into a world where someone could look up and wonder where everything came from. For more than 13 billion years, that light traveled. Across expanding space, through eras of star birth and star death, past galaxies growing, merging, spinning, and changing, past clouds of gas collapsing into suns, past black holes feeding in silence, past the long creation of the cosmic web. It traveled while the Milky Way was still becoming itself. It traveled while the future solar system was only a possibility inside older generations of stars. It traveled while Earth formed, cooled, grew oceans, raised continents, carried life, and eventually carried minds capable of asking questions. And finally, after crossing almost the entire history of the observable universe, that light touched a golden mirror floating in the cold. James Webb did not hear it. There is no sound in that distance. It did not feel it. It did not know what it had caught. But its instruments measured the faint signal, split it into wavelengths, translated it into data, and sent it home. Then human beings looked at that data and realized something strange. The beginning was not as quiet as we thought. At the edge of time, Webb found galaxies, not just one or two isolated sparks, but signs of a young universe already filled with activity. Galaxies shining earlier than expected, stars forming with surprising power, chemical traces appearing sooner than the simplest timelines allowed, black holes possibly growing in hidden centers, little red dots scattered like embers across the ancient dark, a cosmic fog clearing under the pressure of the first light. The story is not finished. That is the most honest ending. We do not yet know exactly what Webb has revealed. Some of the early galaxies may turn out to be less massive than they first seemed. Some of the light may come from hidden black holes. Some of the strange red objects may be dusty galaxies, compact starbursts, young active nuclei, or something still waiting for a better name. Science will correct itself. That is what science does. The first surprise becomes a question. The question becomes a measurement. The measurement becomes a debate. The debate becomes a better model. And then, one day, a new telescope looks deeper and begins the process again. But even if every number is refined, even if some of the early claims become softer, even if the word impossible slowly disappears from the headlines, the deeper truth remains. Webb has shown us that the first chapter of the universe is more complicated than we expected. More crowded, more active, more alive with formation. The universe did not wait calmly in darkness for very long. It began building. It began shining. It began turning simplicity into complexity. And somewhere in that first billion years, the ingredients of everything later began to appear. The first stars forged the first heavy elements. The first galaxies gathered the first great structures. The first black holes may have shaped the first neighborhoods of stars. The first radiation burned through the hydrogen fog. And all of it happened in a universe still so young that, on the cosmic clock, it had barely opened its eyes. That is why Webb's discoveries feel so powerful. They do not only tell us about distant galaxies, they tell us about origin, about how the universe learned to become the universe we live in. Every galaxy Webb sees at the edge of time is part of our ancestry, not in a simple, direct way, but in the great cosmic chain. The atoms in your hand were not made in the Big Bang. The Big Bang made mostly hydrogen and helium. Everything heavier had to be forged later, inside stars and stellar explosions. Carbon, oxygen, nitrogen, iron, the chemistry of life, the dust of planets, the minerals of Earth, the blood, breath, and bone of living things. So when Webb studies the first galaxies, it is not only studying things far away, it is studying the beginning of the process that eventually made places like Earth possible. The first light was not separate from us. It was the opening movement of the same story, a story that leads, after billions of years, to a quiet blue planet orbiting an ordinary star, to oceans reflecting moonlight, to forests breathing under the sky, to sleeping cities, to human beings building a telescope and sending it into the cold so it could look back toward the first dawn. There is something almost impossible gentle about that. The universe made eyes, and then those eyes looked back at the universe. The universe made questions, and then those questions turned toward the beginning. The universe made mirrors, and one of those mirrors is now floating almost 1,000,000 miles from Earth, catching ancient light that would otherwise pass through emptiness forever. And what did that mirror find? Not certainty, not final answers, not a clean, finished diagram. It found wonder. It found that our best models are powerful, but incomplete. It found that the early universe was not a simple darkness waiting to become interesting later. It was already interesting, already changing, already working. At the edge of the observable universe, Webb did not find a wall. It did not find an ending. It did not find a final border where reality stops. It found a horizon. And a horizon is not the place where something ends. It is the place where our seeing ends. Beyond it, there may be more galaxies, more space, more history whose light has not reached us and may never reach us. The universe may extend far beyond the circle of what we can observe, carrying regions we will never touch, never see, never name. That is humbling, but it is also beautiful, because inside our small observable window, we have already found more than enough mystery to fill a lifetime, more than enough to keep Webb watching, more than enough to keep scientists awake at their desks, comparing spectra, testing models, asking whether the first galaxies were brighter, whether the first stars were stranger, whether the first black holes were born heavy, whether the cosmic dawn came sooner than expected. The answers will come slowly, not all at once. The universe is old, and it does not hurry to explain itself. But photon by photon, Webb is bringing the beginning closer. It is turning darkness into data, distance into history, red light into a map of the first morning. And perhaps that is the quiet gift of this telescope. It does not make the universe smaller. It makes our questions larger. Before Webb, the edge of the universe was a phrase that felt almost unreachable. Now, it is a place of faint red signals, early galaxies, hidden engines, and delicate clues. A place where the first structures rose out of darkness. A place where the universe appears younger in time, but older in behavior. A place where our certainty becomes thin, and wonder begins to show through. So tonight, as you imagine that golden mirror drifting in the cold, think of the light it gathers. A photon leaving a young galaxy, traveling through the early fog, crossing billions of years, passing through the darkness between galaxies, avoiding stars, dust, planets, and time itself. Until finally, after nearly the whole age of the universe, it arrives. Not loudly, not dramatically, just as a tiny signal, a quiet touch of ancient light. And in that signal is a message. The beginning was not simple. The first dawn was not slow. The universe was already becoming itself before we thought it had time. That is what James Webb saw at the edge. Not destruction, not danger, not the end of space. It saw a beginning that was brighter than expected, a history that moved faster than we knew, a darkness filled with hidden work, and a universe still whispering, after 13 billion years, that we have only just begun to understand it. At the edge of the observable universe, James Webb did not find the end of space. It found the edge of human understanding. And beyond that edge, the first light is still whispering.